So today's problem is going to be the find minimum in rotated sorted array. First of all, you're going to be given an array of length n, which was originally sorted in ascending order. It has been rotated between 1 and n times. So in this case, our example original array is 1, 2, 3, 4, 5, 6. And if this array has been rotated once, then every number will be moved one position to the right. So 1 would go here, 2 would go here, 3 would go here, and so on and so forth. And then for the final element, where it has nowhere to go, it actually wraps all the way around to the first index. So with a single rotation, this array becomes 6, 1, 2, 3, 4, 5, right? And with 2 rotations, it'll be 5, 6, 1, 2, 3, 4. And in this example, where there's 4 rotations, you can imagine that it'll be 4 wrapping around here to the front, followed by 3 also wrapping around to the front. So that'll give us 3, 4, 5, 6, 1, 2. And of course, if you do it 6 times, which is going to be the length of our original array, it's going to go all the way back to the beginning like so. Now, our input is just going to be a single rotated array. We don't know how many times it's been rotated. This is not information that's privy to us. So for now, to simulate the actual input, I'm just going to assume that our input is going to be this. This is all we're given. Every element in the rotated sorted array nums is unique, yeah? And then our job is to return the minimum element of this array. And they want us to write an algorithm that runs in O log n time, right? So, okay, a couple pieces of information here. First of all, is that everything here is unique, which means that when we want to find the minimum element of the array, there's only one minimum element, okay? So that's one thing that we have to keep in mind. And the second thing is they want us to do this in log n time. So they want us to do some kind of search in this input, and they also want us to do it in log n time. And well, the input is actually sorted. Well, it's sorted and rotated, but it was originally sorted. And with these conditions, it seems like a binary search problem to me, especially with this log n and sorted conditions. I think it's a good case to try binary search at the very least. But the input is a little bit funky, so we'll have to toy around with adjusting our binary search to make it work. Let's give it a go. Okay, so let's say we're given an input of this. So in just normal binary search fashion, I'm going to initialize the low and the high pointers, and I'm going to calculate the mid value, right? Now, what we want to do is that we want to narrow down and find the minimum number. And binary search usually works by dividing up our input into a left and a right subarray, and continuously throwing out 1/2 of the array at a time until we narrow down at our answer. And the way we do it in this question is no different. So now the fundamental question is, how do we know whether the minimum number is going to be on the right side or on the left side? Well, what's interesting about rotated arrays is that 1/2 of the array will be in a nice orderly ascending fashion, and then in the other half of the array, it's going to ascend until it hits our minimum number, then it's going to descend, and then it'll ascend again. But ultimately, since we only have these 3 variables, we don't actually know what's going on in the middle, right? But with just these 3 pointers, we can figure out which half of the array is ascending and which half is not ascending, can't we? So I'm going to write some code, some scaffolding code, initializing our pointers first, writing a while loop with no set exit condition yet, and then just writing the code to calculate the midpoint. Now, as I was alluding to earlier, we know that the flip is going to be here, and with just mid and high, I can see that if this number here is smaller than this number here, that means that the flip would happen over here, right? It would happen in this half of the array. That means that we can completely disregard everything to the left of mid, right? And likewise, if we have an input like this, then when I do the same check, hey, is this number smaller than this number? Well, it is, right? Well, that means that this is going up in a normal ascending order, and there's no flip here. If there's no flip here, then it must be the case that there is a flip on the left half of the array, which means we can disregard all of this, right? So let's write that code. If nums mid is greater than nums high, this means that the right half of the array is not sorted properly. In that case, I'm going to disregard all of this, and I'm going to move my low pointer to here. And otherwise, like in this case, then we're going to move high down to mid, correct? We're going to move high here, and all of this we disregard. So let's have a look at this example again. And then next, we calculate the midpoint again. We check this subarray and this subarray. So we do this if check, and we find out that the mid is greater than the high, which means that the flip happens here, right? So we're going to move low up here. Once again, we calculate the midpoint, check which side is not ascending. It checks the right side first, and mid is actually smaller than high this time. So the abnormal half has to be this one, right? So the else block executes, and our high goes down to our mid. And here's where things get a little bit funky. We're gonna check whether mid is greater than high. Well, it is, right? 6 is greater than 1, right? So that means we have to narrow our search and we have to move low, right? But the thing is, in our code, it says low equals mid, and mid is already at low. So what happens here is that, well, low is just gonna get moved to itself, and it's gonna run this check again, and then this block's gonna execute again, and then low is gonna repeatedly go to itself. And this is an infinite loop. So how are we supposed to deal with this? Now, the way we do that is actually quite subtle. All we need to do is put a +1 here. Why is that? Let's have a think. If this number is greater than this number, then this number cannot be our answer, because if the number at mid is greater than anything, that number by definition cannot be the minimum number of our array, right? Such as in this example, the number at mid contains our answer, right? The minimum number. And because it's the minimum number, like, it's physically impossible for this number to be greater than any other number. So when this clause executes, we know for a fact that the number that we're checking at mid cannot be our answer. Just to really drill it in, I'm going to show you another example. Let's say it goes like this. Mid is not, this number is greater than this number. This block executes. So therefore, this number cannot be our answer, right? Because it's greater than something. So it cannot be the minimum. And with the addition of this +1, we're actually a lot more considerate about how we narrow down our search spaces. And I think this is really important in binary search questions. Really thinking about where our low and high pointer should be. Should it be at mid? Should it be at mid +1? Mid -1? Actually, it's not set in stone. It could be different depending on the question that we're working on. So like in this case, we can't add mid -1 here because, for example, like here, where mid value is our answer, if I add a -1 here, right, it's gonna move high to here. And then our search space no longer includes our answer, which is wrong. So you can see the asymmetry here of this question. I should move down to here, where the old mid was standing. So next time you do a binary search problem, really think about where should we move the low and high values. We shouldn't just autopilot and put a +1, -1, or just put a mid. Back to our original example. Let's see our algorithm in action one more time. So first of all, this block executes. So low gets moved up to mid +1 over here. And then we calculate the mid again. And then we check this, and this is sorted. So the else block executes, and we move high over here. And we're back in this situation once again. So what happens here? It's going to get mid here, and it's going to check whether this number is greater than the number at high. And it is greater. So that means the number at mid cannot be part of our search space. So we want to move our low here, right? So now they're both pointing at the same number. And when they're pointing at the same number, because we've continuously narrowed our search space to get rid of every number that cannot be the minimum number, when we arrive at just a single value, we know for sure that this number is 100% our answer. This number is 100% the minimum number, which is why I'm going to change the exit condition to say while low is greater than high. So we keep going until low and high point to the same number, in which case we can return the number at low. And that's going to be our answer. And like what I said about autopiloting again, this low to high in normal binary search questions, we actually write low less than equal to high. And we keep going until they cross over, right? But here we actually stop when it's reached the final element. And these kinds of things really do vary from case to case. So do be aware of that. Autopiloting the while loop is also a common pitfall, which is why when I solve binary search problems, I don't really commit to a exit condition. I just write true until I go through the entire algorithm, and then I really understand what the exit condition should be. So, okay, we know this works on a rotated array. Well, hypothetically, the same code should still work on the edge case where it's not rotated. So it checks whether this one is ascending. Well, it is ascending. It means that our minimum number will not be here, right? And so the else block executes, and we're going to move high over here, including this number, because there's still a chance that this number is our minimum number, right? And then we calculate the mid value once again, and then we check whether this one is ascending or not. It is ascending, okay? So because it's ascending, our answer can't be here, right? Our answer can't be here. So I'm going to narrow down our search space to over here. And then we calculate our mid. It's going to be here. And then we check this and this, all right? Is it ascending over here? Well, it is ascending. So our answer still can't be that. So we move the high value here, and then we've reached a single element. So even in our edge case like this, just constantly getting rid of all the numbers that cannot be our minimum number will eventually lead us to the real minimum number. And I think that's really cool. So let's talk time and space complexity. We know that this binary search is going to happen log of n times. Okay. And what about our inner operations? Do we have anything expensive? We have this calculation, which is O of 1, an if check, which is just comparing two elements of an array, which are O1 operations. This is an O1 operation. This is also an O1 operation. So everything here is an O of 1 operation. So this entire loop is log n. So that's going to be our time complexity. And as for space complexity, we have the low, high, and mid pointers, which all just hold a single integer. So space complexity is O of 1. And that's going to be your code. Let's try it out in the editor. All right, so let's give it a go. All right, and that's about it. Thanks for watching. Okay, bye.